is a molecular biologist at Massachusetts General Hospital and a professor of genetics at Harvard Medical School. He's one of the discoverers of gene regulation by microRNAs, and he's also involved in the design of an automated genome sequencer to be used on Mars. Okay, so Gary, maybe we'll start with you. So the idea of panspermia, that primitive life spreads between planets, usually involves asteroids landing and sending biological material into space. The debate about whether life began on our planet has been going for a long time, whether it began that way. What is your personal view?
I don't think there's that much of a debate on whether life evolved on the planet. I think it's sort of the dogma that most biologists would believe from the evidence is that there was an earlier RNA world, and 99% of them would believe that RNA world was here, and that the primordial soup on which chemicals polymerized into membranes and biochemistry and metabolism and finally into DNA all happened here.
Well, the question was about panspermia, right? So
right, but so the other side of it would be, oh, it didn't happen here, and life just sort of came to Earth.
Yeah.
And most biologists would say that's a very cowardly view. It's just putting the problem somewhere else, and it is cowardly, but it might be true. And the reason that so I happen to subscribe to that view, but it is a minority view. And the reason I subscribe to it is that if you look in the fossil record, and where you first find sort of bacteria-ish things, where the general view is bacteria are quite primitive, which is wrong. Bacteria are way better than we are. They've transformed our planet. They've made an oxygen atmosphere. They do planetary science on a planetary scale, more than astronomers and planetary scientists do. But so that they happened, they were found within a few hundred million years of the cooling of the Earth. So that would suggest that you go all the way from raw chemistry to real biology in a very short period of time. So you would have to say evolution all the way to bacteria is really dead easy, and it's going to happen over and over and over again. Or that Earth is just a rich medium, and bacteria-ish things came from afar.
So a few hundred million years is too short of a period of time for you, and a few billion years is good enough. So this is this range.
Right, because it only buys you. If life came from somewhere else, you get 10 billion years or so.
Right. But that's enough time for you to do.
Well, I wish it was a factor of 100 and not 10. Sorry. Exactly. I'm against the Big Bang.
Natalie, I don't know whether you're familiar with this paper of last week from Edinburgh University, found that you maybe even don't need meteorites to spread life. The fast-moving particles are enough. What do you think about this?
So panspermia is this idea that life could have originated someplace else and then been spread to another planet. And it can do that either through collisions, lofting material into the air and letting it go on a course through interplanetary space, or as you've mentioned in this other paper, through more recent bombardment by dust in the upper atmosphere. It's seemingly counterintuitive, actually, when we consider this. It sounds kind of crazy, until you stop and realize that planetary formation is a very dynamic process. The early solar system, early epoch of planetary formation, you had planetesimals that were dynamically interacting both with each other and with their nascent disk. So it was a very violent and dynamic process, and that gas and dust clears out rather rapidly, but even today we have this remnant material. So you go through the calculations and you say, yes, it's possible, but I guess I would ask, is it necessary? I agree with Gary's viewpoint that it kind of violates an Occam's razor, if you will. I don't think it's necessary. Moreover, in the solar system, the process takes hundreds of thousands of years, so it's very slow. It's not very efficient. I find this technique much more intriguing on some of these other planetary systems that we found, like the TRAPPIST system, where you have 7 planets packed dynamically into an area that fits within, let's say, Mercury's orbit. So there, the transfer process is like decades, 100 years, not 100,000 years. So I think in systems like that, it's much more compelling.
And can you help me to visualize? So let's say there is asteroid coming in the atmosphere. Obviously, it's very hot. The temperature is very high. And let's say there are some bacteria traveling there. So are they going to survive this last phase?
Well, that's the question, whether you're talking about a collision, which is very violent. So an organism, and we can think about either life, actual microbes, or maybe just organics. If we can take these complex molecules and allow them to survive these violent processes so that they can then seed life someplace else.
How they will survive?
Well, it's challenging. They're going to have to burrow themselves into the lithosphere of an object. They're going to have to survive.
So they should be a little bit underground, right?
Yes, that's right. And during their interplanetary voyage, they probably also have to be buried within, within the rock and then released rather gently as they collide back on the other planetary surface. So, the odds of that happening are small. It's difficult, but calculations say that it's possible. I'm convinced that it's possible, and that these events happen frequently enough during the formation stages and even later stages of the solar system's life that it's possible, but hard.
So, Gary, do you agree that you kind of need to sit inside this rock and hide there for a while and then survive the landing?
I mean, an asteroid, smallish, few meters across, coming towards Earth, is at 80 degrees Kelvin. Enters the Earth's atmosphere. Yes, it gets very hot. Where at the crust, it smalls off. The center is still 80 degrees Kelvin, right? Now, when it collides, there's a lot of energy released, but there's shock waves where there isn't heating. And Jay Malish has done lots of calculations, even experiments on this. So transfer of life by meteoritic exchange, it's hard, but it's not impossible. The other thing to keep in mind is that this revolution in exoplanets that you've been so involved with, it's been magnificent. It has all these hot Jupiters that are spewing planets like crazy. So the movement between star systems can be entire planets. It doesn't have to be pieces of rock. If Earth got ejected tomorrow, yeah, we wouldn't do too well, but the bacteria on Earth would do just fine, thank you very much. And for a billion years to sort of hang out, they could do that.
Meaning that the Earth could be older than 5 billion years. In that case, the Earth would be older than 5 billion years.
Oh, I'm not saying Earth was captured, but it's something analogous to Earth. Could see
Something like that.
Yeah, it could go to the next planetary system. And every star has an orbit belt around it probably, and those orbit belts are very loosely coupled and exchanging like crazy as the stars sort of sweep next to each other.
Lyman, to sort of put some boundaries on how early in the life of the universe life could have emerged. We know that the universe is roughly 15 billion years old, 14 billion years old rather, 13.8, 13.8. So at what period of time we can assume that now life can emerge from what we know?
So something like that the first stars have to form to make these elements of life. So something like 1 billion years, the process could start. And as we've heard about earlier, early on is also a great time because you don't have to travel these great distances. Things are closer together and moving around a little more. So they could well start then and end up here, whatever, 13.8 minus 1 minus 4.5 billion years old.
Okay. So basically now universe life had about 13 billion years to develop. So Gary,
just one thing to add to keep in mind is the one thing that panspermia offers you is the ability to use what you know to look for life. Without panspermia, you'd say, oh, well, maybe there should be genetic storage. And genetic storage could be anything. But with panspermia, you say, let's look for DNA. And we have a $1 trillion industry that's really good at looking for DNA. So isn't it stupid to not look for DNA? Because we have such a great sensitive ability to do it. We can find criminals with their DNA.
Now, again, assuming panspermia is the way to go, which you've been convincingly arguing, do you believe it's more likely that life here could have come from the other star system, like with this object which is now moving across the solar system that we all read about in the last few weeks, or you think it's more likely that it came from another planet orbiting the sun, like Mars? I mean, you're doing Mars sequencing.
The only place you can go, or some of the outer planet moons. You're not going to go to, or you want to go to Alpha Centauri. I can't imagine going to Alpha Centauri to look for life, but you can go to the nearest planet to look for it. So exchange between Earth and Mars is sort of the most narrow view of panspermia. It's sort of bispermia, and so it's not nearly as it doesn't matter you all that much because it's pretty much anthropocentric, right? So, if you're privileging Mars, you're not much different than privileging Earth. So personally, I'd rather it came from somewhere across the Milky Way. I wouldn't posit it coming from Andromeda.
I feel like Gary needs some balance here.
Yes.
So what you're saying is that the exchange between galaxies is basically out of the question, right? So it has to be within.
I can't imagine it, but early on.
But why is it necessary? I mean, the building blocks of life are everywhere, right? We look out into the interstellar medium, and there's already the seeds of complexity. We see them everywhere in the solar system. Carbon has very special properties. Water has very special properties. Why wouldn't the physical processes operate the same everywhere? Why do we need to invoke panspermia? I would ask. And going back to the question of the age of the universe and how quickly does life take a toll, I just wanted to point out one factoid that we now know, that there are planets that we have observed that are as old as the galaxy itself. That is, the galaxy formed in those very nascent moments of galaxy formation. Planets were already forming. The building blocks of planets were already there. And I would contend that the building blocks of life also were already there. And life should have taken a toehold almost immediately.
In a given galaxy.
In a given galaxy, that's right.
And it existed 10 billion years earlier.
Right.
Well, on that subject, let's assume that galaxies are isolated. There's no change between galaxies, at least at this point in time. But within galaxies, it's very easy to get going relatively early on. So this would mean that in pretty much all the galaxies, something should be going on. And in fact, there was this astronomer, Jason Wright, who did the survey of galaxies, looking for signs of civilization. So his assumption was that those Dyson spheres would be visible in infrared spectrum, and if there are enough of those spheres in the galaxy, then there will be some additional radiation coming in infrared. So he looked at those, at the number of galaxies, and didn't find any sizable anomalies. So Lyman, what do you think about that type of experiment?
I was going to say, just backing off, galaxies do interact, right? We see it all the time. We see trails from galaxies, smaller galaxies passing through ours. So I think there can be transfer there. But what are the limits? So I heard about this, and I think ultimately the limit, and I don't know much about Dyson spheres, but it seems like getting rid of the energy. I don't see any limit to making energy. It's how you get rid of it and survive. And so this is how it makes complete sense to me. That's how you look for it, right? Is to look for this infrared emission, and that you don't see it or put some limit on it. That's the size of another civilization could be. So that would mix.
But that demands civilizations to have gigantic planetary scale energy harvesting.
Yeah.
Bacteria don't do that.
Well, the idea is to look at the craziest things we can imagine first, right? Because they're the craziest things. I mean, we have this Kardashev scale that was hypothesized that, we need energy. Complexity needs energy, and technology needs energy. So the idea that on a planet, maybe we will evolve to the point where humans can make use of all of the incident radiation from our star, the sun. And imagine taking that a step further and saying, well, maybe one day we'll be so complex and evolved, we will need energy, we will need to harness energy from the entire sun. And then Jason Wright took it further and said, well, maybe you can keep growing that complexity and evolution exponentially, and maybe you get to the point where you would want to harness the energy of an entire galaxy, or you would have life capable of harnessing the energy of an entire galaxy. And it sounds crazy, but it's worth looking, right? Let's go out and look at the galaxies. We certainly have surveys that have done that, and the WISE survey was one that did that. And look at the galaxies and see if you see anything weird. Are there any galaxies out there where there's anomalously low optical radiation emanating from stars, but a mysteriously high infrared radiation that's in the form of waste heat? So he did this study, and again, it might seem crazy, but it behooves us to go out and look. And as you might expect, he didn't find anything unusual. Okay, but so what, right? It doesn't mean that life isn't out there in abundance. It just means that these galaxies, or these civilizations that maybe have learned to harness energy from the entire galaxy are not common.
So any other signs of sort of stellar or galactic civilizations we should be looking for?
Optical SETI. Heard about it this afternoon, right? Something we should be looking.
But looking for atmospheres on exoplanets is asking for sort of material like what happened here with the production of oxygen. That's very promising.
Yeah, there's different pathways for looking for life. And the one that I'm most tied to is the search for biosignatures. So looking for a global biosphere. That is a planet that has really become where life has transformed it into a living world so that you could see the global effect of life on the atmosphere. That's one pathway. And then you've got the SETI pathways, which also kind of bifurcate. You've got SETI searches that are involved with communication, trying to hear technological signals. I think that's what most people are aware of when they think of SETI. But there's also this idea of artifact SETI, where you look for these kinds of structures of maybe life trying to harness energy from a star. And Kepler actually found a star called Tabby's star that maybe you've heard of in the news, which has some inexplicable behaviors. And astronomers have put forward the idea that maybe what we're seeing is the interaction of some kind of Dyson sphere or megastructure around the star. Most astronomers you talk to are going to say, no, that's probably not what's explaining it. Nevertheless, we can't yet, even today, explain its behavior.
Wasn't it actually ruled out already?
What's that?
Wasn't it actually ruled out already?
It's ruled out on the basis that there's no excess infrared emission that we see from the system. Yeah, but it's also still very mysterious. You could also say, well, maybe they're doing something with that infrared radiation. And I think the point is that you want to look at the universe, and as you're exploring, you want to look for the outliers and think big. Consider all the different possibilities, because life in some weird form might be right underneath our nose.
What about our solar system? What are the prime candidates for the favorite form, the favorite Gary's form, which is bacteria? We probably know that there's no intelligent life here other than our planet. So what are the prime candidates for maybe a simple life?
Well, there's the moons of the outer planets, and Mars are the sort of prime candidates. And the amazing thing, NASA does these things called decadal surveys, where they decide, okay, the next 10 years, what do we want to do? And as a community, they sort of do a poll of what we want to be telling NASA to build. And the amazing thing, at least in planetary science, is that looking for life is their number one goal. They've become life scientists, which to a life scientist is inspiring and right on, But the astrophysics part of NASA, too, exoplanets is the hottest thing at NASA. So the whole agency is a life science agency now. It's stunning.
No joke.
Cosmology left out.
I'm sorry.
A 10th objective was just added to NASA as an agency, which is the search for evidence of life beyond Earth.
So Natalie, what are your prime candidates
in the solar system?
Top three.
We don't see any evidence of another global biosphere, right? At least not that's we've flown by all of the major objects, so we don't see any evidence of a global biosphere. But life could be lurking in niches, and I think the favorite niche where life might be lurking is in these subsurface oceans in the outer moons, like Enceladus and Europa. And depending on which scientists you talk to, they each have their favorites. Right now, legislators are pushing towards exploration of Europa, but actually both Cassini and Hubble observed these geysers emanating out of Enceladus. So there's direct evidence that water is heated from underneath and is erupting through the ice surface on Enceladus. But just to give you some perspective.
What is your favorite?
What's that?
Europa, Enceladus.
Enceladus is the one where the geysers are very prominent. Europa also has geysers, but they're not as well understood as the geysers on Enceladus. The geysers on Enceladus are driven by tidal heating from underneath inside the core of the planet, and that process is very well understood. The geysers are very predictable and very strong. Europa also seems to have some geyser activity, but it's less well understood. Europa, though, is easier to get to because it's orbiting Jupiter. The other thing to put into perspective, maybe you've seen these graphics where they show a picture of a planet or an object in the solar system, and then they draw a little bubble that shows how much water content it has on its surface. So if the Earth is like a basketball, its whole water content is like the size of a marble, okay? The moon is about 3 times smaller, maybe like the size of a baseball. Enceladus is actually the size of a marble in this model. It's very, very tiny. It's like 7 times smaller than even our moon. So I don't know. My favorite place where life might exist, I think that we should go explore Enceladus first because that's the one that we understand the best. But I'm also very intrigued about Europa. I think that there could be life in the oceans that we can't detect remotely, that we have to go and explore.
And you can also fly through the plume of Enceladus, so you don't have to land on it to look for life. So it's really very attractive.
You look for RNA or DNA?
Absolutely. Yes.
Gary, and your favorite seems to be Mars. And I understand on Mars you need to go underground to find something, right?
For water, yeah.
No, to find like bacteria, RNA, whatever it is.
Well, but the bacteria below across the Earth. Of course, we have a lot of it, but under the polar caps, there's a lot of water in the polar caps of Mars. And so you can imagine aerosols blowing bacteria around, and you can detect bacterial DNA at a very low concentration.
So you don't even need to dig.
No, it's just, yes, it's high radiation, but radiation's UV is an oxidizing atmosphere, and oxidation is good, right? You can pass electrons to terminal oxidant. Organisms are very good at dealing with DNA damage, and they've had a few billion years to adapt, right? So the organisms that Mars had an atmosphere probably when it was verdant with life, I would guess, and life has probably adapted, assuming it hasn't gone extinct, and that's a possibility that, yes, it did completely go extinct, but I would always bet on life as opposed to against it.
So you're trying actually to design a sequencing machine that you can put on the surface of Mars to look for this low concentration elements, right?
The way people now look for life on Earth, if you go to a lake, a dry valley in Antarctica, and you want to know what's there, the way it's now done is you make DNA, assuming there's DNA there. You do random sequencing, and you find out all the organisms that are there by the array of DNA. You get all the genes at once. It's all doable. It can be done in the field.
In the air?
You can do it in the air. You can see what organisms live in clouds. I mean, the surveys that are going on Earth now, metagenomics, there's 10,000 papers that have done this. And at a certain point, we're not there yet, but at a certain point we will have a lookup table of everything on Earth, right? We'll know every organism with all the variation, because the sequencing we're doing is accelerating at an enormous rate. And so at some point you'll be able to say, oh, look, what we found on Mars is not on our lookup table on Earth. We're not there yet. But, the prediction is we'd see deeply branching, right? Because we have a tree of life on Earth, and everything sort of fits into that tree of life, and Mars would be sort of like what kangaroos are to, North European fauna, recognizable but different.
And how big your sequencer is going to be?
Well, the Oxford Nanopore is an English company that builds sequencers based on nanopore technology, where the DNA goes through a pore, changes its conductance, it weighs 80 grams. There's thousands of these in the field. There's a very enthusiastic user base that goes out and sequences in ponds, and people who have the flu, and it's used constantly for all kinds of things like that. So that's something that could be just massaged a bit. But, NASA has to agree. It's a very high-risk thing, right? Because if you go to Mars and say you're going to look for DNA, you could come up with nothing. And they like to send instruments that will give a spectrum, a picture, mass, something, an oxidation state.
Well, now there's one other person to talk to, Elon Musk.
Yeah, I've been trying.
Right. But that's the rocket instead of the Tesla.
Yeah, it's way better than a Tesla, much better than humans.
Maybe I can help you there. But I know earlier today we talked about a more simple strategy of trying to find the signs of other type of life on our planet. So maybe it's hiding somewhere where we didn't look yet. So why go elsewhere? Let's just try to see any pockets where alien life can exist. Do you think it's a reasonable strategy?
Yeah, so the modern genomics of DNA world life, material life, sees evidence of the RNA world, of sort of the precursor, and there's lots of layers of that in our genomes, of living fossils from the RNA world. And so that world was mostly displaced by the DNA world, but the question is there a refugia somewhere where you could see a kind of a living fossil of the RNA world? And, you might want to look in the environment that looks the most like the Earth 3.5 billion years ago. And one of the beauties of Mars is that it doesn't have plate tectonics, and so, we are constantly erasing our history with this continental movement that doesn't exist on Mars. And so you might actually have the remnant of the RNA world there if that's what was actually exchanged between the two. And that would be the most gorgeous thing to discover on Mars, is to be able to do archaeology of bacterial history. I'm not saying it will. It's just that's a prayer.
Lyman, so it seems like the universe might be teeming with life of some sort, at least simple life, and occasionally intelligent life. But from the standpoint of a physicist, how long do you think can life survive in our universe?
See, so if this model we have is right, and we extract it, and we don't end up in a big rip, we'll end up in a long phase of hundreds of trillions of years of a pocket of about 1,000 galaxies, something like that. And who knows what's going to happen after that, right? I mean, who knows whether physics will come in. But with the accelerated expansion, right, things move away, but we'll end up with something like that that's sort of gravitationally bound.
So so basically you give us a few trillion years, right?
Yeah, more. 100 trillion.
Okay. On that note, thank you very much. We'll go to the next panel. In the next hour and a half, we are going to take a look at some of the big questions in science. And we will be asking the following: how much can we know? How far can life go? And is nature simple? So, three relatively big questions. And we are joined today by the new Breakthrough Prize laureates, as well as the laureates of the previous years, representing three fields of physics, life sciences, and mathematics, as well as NASA's most celebrated astronomers. So, I would like to bring here on stage for the first panel Carl Deiserov, Christopher Haken, and Cameron Buffer. So Carl is a professor of bioengineering, psychiatry, and behavioral sciences at Stanford. He is a pioneer of optogenetics, a way of controlling neurons with light, and clarity technology for making brain tissue transparent to enable detailed imaging. Christopher is a professor of mathematics at the University of Utah. He works on projective varieties, a branch of algebraic geometry with a focus on high dimensions. And Kamran Vafa is a professor of theoretical physics at Harvard University. He is one of the leading figures in string theory and has produced many important and original insights into space-time geometry and black holes. So, discussion one, how much can we know? So, Carl, we human beings evolved to survive in Africa and savannah. How is it that some of